Welcome to example number 6 and the concept of buoyancy. Buoyancy is a pretty familiar phenomena. If you've ever had to lift a boulder when it's in the water versus when it's out of the water, you should have noticed that there's a difference in this weight that you feel. The weight of it while it's in the water feels less than it is when it's in air. And that's because there's this extra additional force in the water called the buoyant force. This concept was initially discovered by Archimedes, who's from the 3rd century BC. And what he stated was that when an object is completely or even partially submerged in a fluid, the fluid will exert a net upward force on the object that is equal to the weight of the fluid that has been displaced. So to understand the buoyant force and where it comes from, take a look at the diagram on the right side here. So we know that the forces that act to the sides of this would be equal and opposite. However, the force on the top surface and the lower surface are not the same. Now remember that pressure is equal to force divided by area, so the force on the upper surface would be the pressure at that upper surface times the cross-sectional area A here. And the force on the lower surface pushing upwards would be equal to pressure 2 times area. And pressures here and here are not the same. If you recall, the pressure is equal to the external pressure plus rho GH. And at this depth down here at the lower surface, that's deeper than the upper surface, and hence there's more pressure down here, and hence there's more upward force on the lower surface than there is on the upper surface. And it's the difference between these two forces, F2 minus F1, that creates this buoyant force. And Archimedes stated basically that the buoyant force, which is that net upward force, is equal to the weight of the fluid displaced, which is shown here. So FB, which stands for the buoyant force, is equal to FG, which is mg. Now m can be calculated by, well, you know that the density of, say, the fluid that has been displaced is the mass of the fluid displaced divided by the volume. So we can then replace the mass with the density of the fluid times the volume that has been displaced. I'll just write that as V sub 0. So if the object is completely submerged, this is what Archimedes famously figured out, is that if you wanted to find the volume of an object, you simply push it in the water, and the water that gets pushed out is equal to the volume of the object. So again, the buoyant force is equal to rho Vg. That's the way they're going to write it in the formula sheet. But they're not going to tell you what these two variables stand for. That rho is not the density of the object, but that's the density of the fluid that has been displaced. And that V is not the volume of the whole fluid. It would be equal to the volume of the object if the volume is completely submerged, or V is really just the volume that is displaced. So if it's partially submerged, it's really the volume of the object that's just below the surface of the water, for example. Let's take a look at example number 6 to illustrate this. So we have a gold statue that is being raised from a sunken treasure ship. And we're asked to find the tension of the hoisting cable when the statue is completely submerged within water, and then find the tension when it was completely out of the water to compare them. We should draw a free body diagram as we go through here. So when it's submerged in the fluid, there are several forces acting on this body. So let's go ahead and draw that force diagram. How many forces do you think would be acting on the gold statue when it's submerged in the water? So we've got the tension going up. We have a bit of a buoyant force going upwards. And then we have the weight going downwards that's being balanced by these two forces. So let's assume that y is positive upwards. And we will assume that it's all in equilibrium. So the sum of all the vertical forces is 0. So we have the tension upwards plus the buoyant force upwards, but minus the weight downwards is all balanced out to be 0. So we're trying to solve for the tension. So the tension would be equal to the weight minus the buoyant force. The weight of the statue would be just simply m times g. And the buoyant force would be the density of the fluid times the volume of the object, because it's completely submerged, times g. So we might be looking at this and say, well, yeah, we know m and we know g. And the density of the fluid must be water, so we'll assume the density of water is 1,000 kilograms per meter cubed. But we don't know the volume of the object. You have to find that. That's the volume of the fluid that has been displaced. So the volume of the object when it's completely submerged would be the mass of the statue divided by the density of the statue, because we're looking for the volume of the object here. Remember that density equals mass over volume, and we're just rearranging for V. So the mass of the statue is 15 kilograms, and the density of gold, well, we'll have to look that up. What is the density of gold? So if you go on the internet or look in your textbook, you'll see that it's around 19.3 times 10 to the power of 3 kilograms per meter cubed. And that will give you a volume of 7.77 times 10 to the power negative 4 meters cubed. So now you're ready to substitute it in your expression. So the tension would be equal to the weight, which is 15 kilograms times 9.8 meters per second squared, minus the density of the fluid, which is 1,000 kilograms per meter cubed, multiplied by the volume, 7.77 times 10 to the power negative 4 meters cubed, and g is 9.8 meters per second squared. And that will give you a tension of around 139 newtons. Okay, let's now do part B when it's when in air now. So now, when you have it in air, we really have only two forces. Really just the tension and the force of gravity, and no buoyant force. Well, technically there is a buoyant force in air, but it's very, very small because you're just displacing air, which has a very low density. So the sum of the force in the y is 0, and so we have the tension minus the weight, which is equal to 0. And so the tension is just really equal to the weight, mg. So that's 15 kilograms times 9.8 meters per second squared, which gives you a tension of 147 newtons. And by the way, just a quick note, this is assuming that as the statue is being lifted, it must be going at constant velocity or at rest. Because really, otherwise we wouldn't say the sum of the forces in the y would be 0. Now we could solve this problem and add acceleration, and then you'd have sum of the force in the y equals ma, and then you have to include that into your problem. And that's it for this example.